Hello everyone, welcome to another hands-on engineering tutorial. In this lab, we'll be going over shift registers. Make sure to check out the PDF for this lab, which is linked in the description below. It goes over some additional information about how shift registers work, and has the part numbers on the specific components that we used. Moving forward, we'll assume you know how to read analog inputs, use hardware serial, and do bounce button presses. The shift registers used in this video are serial input and parallel output. That means that the register takes the inputs separated by time, and all the outputs come out at the same time. We've used serial in the past to discuss one method of communicating between the Arduino and our computer. In both cases, serial refers to the fact that the data comes in strings of bits, each sent one at a time. When we used it before, the Arduino and computer agreed on a specific baud rate that said how often bits would be sent. This relied on the internal clocks of both the Arduino and the computer to accomplish this. Communications between the Arduino and the shift register work similarly, but not exactly the same. The shift register doesn't have an internal clock, so we'll have to supply a clock to the device so that it knows when to sample the serial input. This clock is provided as an input to a pin on the register that we'll call the serial clock input. A transition from 0 volts to 5 volts on this pin tells the shift register to sample the serial input line. This is also known as being positive edge triggered. Holding the clock low, holding the clock high, or transitioning the clock from 5 volts to 0 volts won't cause the signal to be sampled. Only the transition from 0 volts to 5 volts causes the shift register to sample the input signal. When the shift register samples the input, it measures the voltage on the serial input line. If the voltage is 5 volts, it records a digital 1. If the voltage is 0 volts, then it records a digital 0. There are 8 outputs on the shift register. The datasheet refers to these outputs as QA, QB, QC, QD, QE, QF, QG, and QH. Upon receiving a clock pulse, the shift register samples the data at the serial input line and places the digital value into QA. The data that was previously in QA is moved into QB. The data that was in QB goes into QC, and so on. The data that was previously in QH, the last place, is moved out and removed from the shift register. This gradual shifting of the data is why the device is called a shift register. Let's run through an example. Assume we've just powered on our device, and nothing's been written to it yet. Our shift register, by default, is filled with digital zeros after receiving power. Now let's say that our register has received the following inputs on its serial input and clock lines. The top waveform is the serial input line, and the bottom waveform represents the clock signal. Above the waveforms are all 8 storage elements for the shift register. These are what's going to be updated when we receive our signal. Remember that the shift register only samples when it receives the positive edge of a clock pulse. Thus, we have to locate all of the positive edges to determine which inputs are going into the register. This is the first positive edge. The serial input line at this point in time is high, which means that it's a digital 1. A digital 1 is placed into the storage space of QA, and all of the other values are shifted to the right. The value at QH is shifted out of the register and disappears. The next positive edge is here. This value is a digital 0. All of the values in the shift register are shifted to the right, leaving a new opening at QA which is populated with the 0. Now our register has, in order, 0, 1, and then 6 zeros inside of it. The animation on screen goes through the rest of the signals. We're left with the register having a final value of 0, 1, 0, 1, 1, 0, 0, 1. There are a few more things we have to discuss about the register. There's actually an additional clock line that will be used to control when the output is updated. This is also positive edge triggered. When triggered, it causes the values from the most recent set of data in the register to move to the output. Prior to this signal, the register's output values won't change, regardless of the inputs. Those values will still be inside of the shift register, but just aren't seen at the output yet. This is useful so that you can cleanly change between 2 different sets of outputs. You must send the update output clock signal to the shift register in order to force the newest set of data to the output. There is also an output enable pin which is active low. This means that it needs to be connected to 0 volts to allow for outputs to work. If set to 5 volts, all of the outputs will be set to 0. The final input pin that we'll cover is the serial clear line. When connected to 5 volts, the register is cleared and set to all zeros. This line must be kept connected to ground if you don't want to clear the register. This is the pinout diagram for the shift register. You should clearly see all 8 output pins labeled. The SCR pin is the serial input data line. This is the line that's sampled and pulled into the register. OE bar is the output enable pin. RCLK is the clock input that tells the register when to sample the input signal. SRCLK is the clock input for updating the output. The SRCLR bar pin is the serial clear pin. The shift register will take 5 volts at its VCC pin, and you should connect ground on the shift register to a ground on the Arduino. There is one last pin on the shift register, and that's QH prime. QH prime is a special output pin that's used to connect multiple shift registers together. QH prime holds the same value as QH, so by connecting it to the SER pin of a second shift register, you can effectively create one longer shift register. Both shift registers should have the same inputs except for the SER line to accomplish this. When a clock pulse is received, the second register will read the voltage on QH prime and take a digital 1 or 0 depending on the situation. Now we can store and control twice as many bit outputs with the same number of digital pins. Let's build a circuit to demonstrate how shift registers work. This is the circuit schematic that we designed. We'll be using 2 buttons, 2 switches, 1 Arduino Nano, 2 shift registers, 16 LEDs, and 16 2K ohm resistors. The Arduino Nano is here merely to debounce the signals from the buttons so that we don't have any strange behavior. In our setup, we'll be using the buttons for the 2 clock signals. The 2 switches are for the serial input of one register and the serial clear lines of both. QH prime of the first register will be used for the serial input of the second register. The OE bar pin is left connected to ground on both registers. QA through QH of both registers are connected to one LED circuit each. Each LED circuit is comprised of an LED and a 2K ohm resistor. Here are some photos of the circuit when it's actually built on a breadboard. This photo shows how the outputs of the shift register should be connected. Make sure that you use at least 2K ohm resistors, as the maximum output current of each register is 35 mA total. Using these 2K ohm resistors guarantees that our total output current stays below that maximum. This photo shows what the buttons and switches should look like when connected to the Arduino. All of the switches and buttons have one pin connected to separate digital pins on the Arduino. The other pin of each of those devices is connected to the ground on the Arduino. We'll set all of those digital pins to input pull up so that we have 2 button states when we write our code. When a specific button or switch is closed, that digital pin will read 0 volts. When open, no current can flow, so the digital pin will see 5 volts. We connected the switch for the serial input line to digital pin 11, the switch for the serial clear pin to digital pin 12, the button for the serial clock input to digital pin 9, and the update output clock button to digital pin 10. This photo shows the connections between the Arduino and the shift register. The SCR input of one of the shift registers is connected to digital pin 2 on the Arduino. The other SCR input is connected to QH prime of the former shift register. The SRCLR bar pins on both registers are connected to each other and to digital pin 5 on the Arduino. The RCLK pins are connected to each other and to digital pin 4. Finally, the SRCLK pins are connected to each other and to digital pin 3 on the Arduino. Now let's go over the code. This is the code that we're using to control the shift register. We begin our code with 8 constant integers, the first 4 of which represent the button and switch inputs. The first 2 are the clock button and the update button. The clock button represents the button used to send the shift register a pulse to read the serial input line. This is connected to digital pin 9. The update button is the button for updating the output of the shift register. This is connected to digital pin 10. After that, we have our two switches, the serial switch and the clear switch. The serial switch is digital pin 11. This controls whether a 0 or a 1 is on the line that will be read when a clock pulse is received by the shift register. Then we have the clear switch. The clear switch is what controls whether or not the shift register should be cleared, if all the values should be set back to 0. This is connected to digital pin 12. Next, we have the four outputs that we're using to control the shift register. They are the serial output, the update output, the clock output, and the serial clear output. In order, they're connected to digital pin 2, 3, 4, and 5. Then we have two unsigned longs, previous time clock and previous time update. Previous time clock is for the debouncing of the clock pulse for the serial input line. Previous time update is for the debouncing of the update output clock line. The other two signals don't really matter if they bounce. This is because the noise generated by the switches don't really matter. Only noise on the clock outputs could cause any real issues with the shift register. Inside of setup, we use pin mode on the four inputs and set them all to input pull up. This will make sure that we have our two states, where if the button or switch isn't closed, then we'll see 5 volts, and if it is closed, we'll see 0 volts. Then we use pin mode on the four outputs and set them all to outputs because we want to control the shift register from the Arduino. Inside of loop, we debounce the button inputs for the serial clock input button and for the update output button. When we know that the button has been pressed down exactly once and it isn't being held down or that it isn't a bounce, we send the clock out to high and then the clock out to low. We know that the clock output was low previously, so by writing high and then low, we're sending the positive edged clock pulse to the shift register, telling it to sample. We send this clock output for both the serial input clock and for the update output clock. The code for debouncing both buttons is almost exactly the same. After debouncing those inputs, we use digital write on both the serial output and the clear output with the digital read of their respective inputs. So sear switch for sear out, and clear switch for clear out. This code will ensure that all of our inputs and outputs work together correctly so that there aren't multiple signals being sent to the shift register when there shouldn't be. This will grant us a greater understanding of how shift registers work and let us use them in future projects. Now let's see what it looks like when the code is uploaded and it's running successfully on our breadboard. Alright, let's demonstrate how the shift registers work. We have our four inputs. This is the clock for the serial input line. This is the clock for the update output line. This is the switch for the serial input line, which is currently set to 0. And this is the switch for the serial clear line, which is currently set to digital 1 or 5 volts. If we were to press the clock and then the update, we should see nothing happen because the serial line is set to 0 and all of the LEDs are currently off. So let's try that. Press our clock, then our update, and right, nothing changed. We can do that as much as we want. We press the clock 100 times, and press update, nothing happens. Now if we switch serial to be a digital 1, then we press our clock. Nothing happens until we press our update button. Now we have a digital 1 in the first LED, so it turns on. Let's press clock twice. 2, then we press our update output, and the next two LEDs turn on. So now we have 3 digital 1s in our register. Now let's see it actually shift down. So we're going to turn the serial line off, then we're going to press the clock line once, and then update output. Now let's press the clock 2 more times, press the update once, and they shifted over 2 more LEDs to the right. We can keep going. As you can see, they keep shifting down the register. Every time I press clock and then update, they move 1 more down. Now let's see what happens when we flip the serial clear switch. When flipped, all of the LEDs are set to off. All of these LEDs will be kept off until you flip the serial clear switch back. However, if you press the update button at any point, they'll also all be set to 0. This points out an interesting caveat when using the serial clear line. You need to make sure to send the update signal while the serial clear line signal is still at 0. Otherwise, the digital signals will flip back to the way they were until you send a new update. Therefore, there won't be a clean transition unless you make sure to send the update output clock signal while the serial clear line is still at 0. Alright everyone, that's it for hands-on engineering. We hope you learned something new about shift registers and how to incorporate them into your projects. Shift registers will allow you to make more interesting designs and add extra outputs to your Arduino. We hope you enjoyed the video, and if you did, please like it, comment, and subscribe to our channel. That's it for hands-on engineering. See you next time.